Alright, so now after going all over the series testing, we're going to review all this in 11.7 strategy for testing series. So how do we approach a series problem? I mean, they're not going to tell you use this method or that method. Okay? So we're going to review all of them so we can just have some tips on which method to use for which series. So here's the main strategy. Here's the main strategy for testing series. The first one is to apply the nth term test for divergence. That's the easiest one, as long as you suspect that the nth term, when you do the limit as n goes to infinity, is not zero, then do that. Apply the nth term for divergence, which is if the limit as n goes to infinity of an is not zero, series diverges. Okay. So here's an example. Page 781 in your text number 4, part A, sigma n equals 1 to infinity n plus 1 over n. Right away, I know that the limit of an is 1. As long as it's not 0, say series diverges by the nth term test for divergence. Okay, so that's the first thing you want to look at. Then if it's a p-series, that's another easy one. 1 over n to the p, n equals 1 to infinity. It's a p-series. It converges if p is greater than 1, and it diverges if p is less or equal to 1. Number 2, page 781, part B. Sigma n equals 1 to infinity 1 over n to the 3/2. It's a p-series where p is 3 or 2, which is greater than 1. So right away we say the series converges by the p-series test. By the way, right after page 60, between page 60 and page 61, I have a handout for you. It sums up all the convergence tests. The nth root test for divergence, the integral test, the comparative test, the ratio, the root, the limit comparisons, alternating, the root, the ratio. Okay, so all these tests are summed up here, and the statement of the test, and when does it converge. Okay, so this is in the notes on D12. Okay, it's in there between page 60 and page 61. So review that. It has all the rules for you. It makes things a lot easier for you. Alright, you may not use this as a cheat sheet on the test. You may not. Okay, but you need it will help you do the work now though. Then the geometric series. So if you have a series that looks ARN minus 1 or sigma ARN, these are geometric series with a common ratio R and a first term A. They converge if the common ratio between -1 and 1, and they diverge if the common ratio is less or equal to -1 or greater or equal to 1. And when they converge to S, which is A over 1 minus R. A is the first term, and R is the common ratio. Alright, so here's an example about geometric series. N equals 1 to infinity 2/3 to the n. So if you write it out, it's 2/3 plus 2/3 squared plus 2/3 cubed, and so on. So it's a geometric series with the first term is 2/3, the common ratio is 2/3. As long as the common ratio is between -1 and 1, it converges to S, which is A over 1 minus R. So it converges to 2/3 over 1/3, which is 2. So that series does actually equal 2. That's the beauty of the geometric series test. It gives you the exact answer should the series converges. Okay, then the comparison tests. There are two comparison tests. There's the direct comparison test and there's the limit comparison test. Okay, as you can see in this handout, this is the comparison test and this is the limit comparison test. So there's two different tests. Okay, so the comparison tests, they apply to series with positive terms. Okay, with positive terms. If the nth term is rational or algebraic function of n, it involves roots of polynomials, then the series should be compared with p series. So if you have a rational function like n squared plus 2 over n cubed plus 1, they're telling you to compare it with sigma 1 over n to the p series, basically. Okay? If the terms are negative, because remember this has positive terms, if the terms are negative, then use absolute convergence, which implies convergence. Okay? So don't worry, you still can use the comparison tests, even though the terms are not always positive, because you could absolute value, and absolute convergence implies convergence. So number 10, page 781. And just to review these tests with you in case you forgot. Alright, so the direct comparison test, you have sigma an, sigma bn series with non-negative terms. You have it's a1, so it's decreasing. You know, a1 is less or equal to b, sigma ai is less or equal to sigma bi. If sigma bk converges, then sigma ak converges, and if sigma ak diverges, then sigma bk diverges. Okay. Now the limit comparison tests is when you do the limit of ak over bk and you get a number between 0 and infinity, then they're both convergent or both divergent. And there's the notes if you want to read this. Okay. Alright, so number 10, page 781, n equals 1 to infinity. So we're going to compare this, it's a polynomial, a rational function. We're going to compare it with a p series and n over n cubed, which makes 1 over n there. That's the trick, okay? It's 1 over n squared. And you can see why. Because n minus 1 is less than n, right? And if you divide by n cubed, it's still going to be that. And if you divide by n cubed plus 1, it's still going to be n cubed plus 1, which this is less than n over n cubed, which is 1 over n squared. So this is sigma, this is an, so we're going to use bn. So we're going to compare sigma an and sigma bn. Since an is less or equal to bn for n greater or equal to 1, and since sigma bn is a p series, it converges because p is greater than 1. That means sigma an converges as well by the p series test. Okay, that's the direct comparison test. Now let's look at the limit comparison test. Here's an example. Sigma n equals 1 to infinity sine of 1 over n. If we use the limit comparison test, we let an be this guy, sine of 1 over n, and we're going to compare this with bn, which is 1. That's all. That's the obvious thing to compare it with. So we're going to do limit as n to infinity an over bn. Limit as n goes to infinity sine of 1 over n over 1 over n. Well, sine of 0 over is 0, and then that's 0, so 0 over 4 gets L'Hopital's. So its limit as n goes to infinity, derivative of sine is cosine, and then times it by the derivative of 1 over n, which is negative 1 over n squared. Same thing for this guy. These cancel out. Limit as n goes to infinity, sine of 1 over infinity, cosine 0 is 1. And the direct comparison test, if you get a number between 0 and infinity, then they both converge or they both diverge. So one is between 0 and infinity, and since this guy diverges, so our series diverges. Since sigma 1 over n diverges. Then the alternating series test, number 5. The alternating series test. So if the series of the form negative 1 to the n minus 1 an or negative 1 to the n an, we use the alternating series test. And let's look at the alternating series test. So it wrote it out, instead of using the sigma notation. So it converges if it's decreasing, a1 is greater than a2, the sequence, decreases, and the limit equals 0. And this test only applies to alternating series, and it's assumed that ak is positive, except, ak is the term without the sign, which makes. So it has to be decreasing, and the limit has to be 0 for this to work. For this to be convergent, okay? So number 26, page 781, sigma n equal 2 to infinity, negative 1 to the n minus 1 over square root of n minus 1. Okay. So if you use the alternating series test with an equals 1 over root n minus 1 without the pluses and minuses, obviously it's positive for n greater than 1, or greater than or equal to 2, and it's decreasing, right? Because a1 is, a2 is 1 over 1, a3 is 1 over root 3 minus 1, a4 is 1 over 1 over root 2 minus 1, and so on. So you can see it's decreasing, or we can find the derivative and make sure it's negative. So if you do the limit as n goes to infinity of an goes to infinity of 1 over root n minus 1, which is 1 over infinity, which is 0, that means series converges by the alternating series test. Next, the ratio test. Which we just went over in the previous section. So this is good for factorial and expressions raised to power. Okay, this is good for factorial, and this shouldn't be used for rational functions. So don't use for rational functions or algebraic functions. Like, don't use for p-series and so on. okay, because it's gonna fail, because limit as n goes to infinity an plus 1 is gonna give you 1, and it fails. So 36 from page 781, sigma n equals 1 to infinity n squared plus 1 over 5 to the n. This is not a rational function because at the bottom we have exponential function, okay? So we can use the ratio test. It has powers of n, okay? So an plus 1 would be n plus 1 squared plus 1 over 5 to the n plus 1. So we're going to do limit as n goes to infinity. I need absolute value because everything is positive. So limit as n goes to infinity, n plus 1 squared plus 1 over 5 to the n plus 1 over n squared plus 1 over 5 to the n. So multiply by the reciprocal, n plus 1 squared plus 1, we're going to times it 5 to the n, over n squared plus 1 times 5 to the n plus 1. So these cancel out, 5. Now this guy, if we work it out, we get n squared plus 2n plus 1 plus 1 plus 2, and this is n squared plus 1, which gives me times 5, which gives me 1 over 5 less than 1, so the series converges by the ratio test. Okay. Next, the root test. Again, we just did that. So this is used for nth terms. If the nth term is a power, okay, it's a power. If the nth term is a power, an equals 0. Powers are a function of n. 42, page 781. Sum from 1 to infinity n factorial to the n. You could actually try also the ratio test for this one because it has factorial. But I'm going to do the root test, which says an, this is an, so we're going to do limit as n goes to infinity nth root of absolute value of an, which is not needed because everything is positive, to the 4 to the n, which would be, you can cancel out the powers, so it's limit as n goes to infinity n factorial over n to the 4th. Remember, n factorial is n times n minus 1 times n minus 2 times n minus 3 times n minus 4 times n minus 5 all the way to 3 to 1. And n to the 4 is n times n times n times n and no more. So if we do this part, limit as n goes to infinity, you get 1 times 1 times 1 times 1, which is 1 times, and that's going to be n minus 4 factorial, which is the limit as n goes to infinity, it's infinity, because infinity minus 4 is infinity times infinity times infinity. And since it's infinity, the series diverges by the nth root test. I guess, again, if you forgot, here's the nth root test. You do the limit of the kth root of uk or a. Series converges if it's less than 1, just like the ratio. Greater than 1 it diverges, or infinity, and then no conclusion if it's 1. Alright, the last test that we're going to review is the integral test. The integral test. So just to remind you, an equals f of n. If you can write the function in terms of a sequence, where the best thing here is if you can integrate the function. Don't even waste your time. It can be easily integrated. Then use this test. And again, let's take a peek. The integral test. So you have to have positive terms, and the actual value of the integral is going to be the value of the series. The function has to be decreasing and continuous. they both converge or both diverge, series and the integral. Okay. And an example about this is number 18, page 781. Sum from 1 to infinity n square e to the negative n cube. I can integrate x squared e to the negative x cubed by substitution, so that's obvious. So if we let f of x equals x squared e to the negative x cubed, this is continuous, positive, and decreasing. You can find the derivative and you can see it's decreasing. Its first derivative is negative. It's in my notes. So using the integral test from 1 to infinity, x squared e to the negative x cubed, it's the limit as b goes to infinity, 1 to b, x squared e negative x cubed dx. Using substitution, we let u equals negative x cubed, then du is negative 3x squared dx. So this would be, so you need negative 3, and then you need negative 1/3, so it's negative 1/3. Limit as b goes to infinity of, so you're gonna have du and then e to the u, so you're gonna get e to the u from 1 to b, which would be negative 1/3 limit as b goes to infinity, e to the negative b cubed minus e to the negative 1. E to the negative infinity is 0. So negative 1/3 times negative 1 over e is negative positive 1 over 3e. So that means the integral converges, and so does the series. So does the series. Okay, the integral converges, and so does the series. And that's it for 11.7. So I'll see you in 11.8 shortly.